Johnny here with Simpson Math, and in this video I'm going to be covering an introduction to comparison tests for improper integrals. Now in our previous video we were dealing with trying to determine if an improper integral would converge or diverge, and we kind of came up with this p-test. So this is a quick recall. Just remember that the p-test states that if you've got some integral from some number to infinity, and that number is positive, so that interval is a positive interval, and your integrand is 1 over x to some power, then the size of that power determines whether it will converge or diverge. We found that if p was larger than 1, it converged. But if p was 1 or less than that, then it would diverge. So the diverge meaning the area sums up to an infinite amount, converge meaning that the area would sum up to some number amount. All right, and I was going to draw little graphs of each of these functions to then compare them, but I think technology will be faster and better than I am. So I'm going to switch over to Desmos, and my note gets smaller, but that's okay. I'm going to type in those functions. So I'm going to start at 1 over x to the negative first power. Now, of course, the negative 1 just reciprocates the x, so of course we're just graphing y equals x. And I think it's clear. I'll kind of zoom in on starting at 1. Of course, if I were to start at 1 and then sum up all that area, can't see me pointing at it, but all that area starting at 1, 1 right here, you draw a little bar down and you sum up all that area, then of course that diverges. Anyone can tell that's all that area will sum up to infinity. So let's do another one. The next in the list, I have 1 over x to the 0. So I'm just increasing the power by 1. And yeah, x to the 0 is 1, so we're just getting the function y equals 1. Just that constant function at 1. And this, I think anyone can tell. If I were to start shading at 1 all the way to the right, up to infinity, I'm just keep adding area, the same amount of area. And yeah, that would just sum up to infinity. Let's keep going. In the next color, let's graph x to a fraction. Something like 1 over 2, yeah. Now, this one, of course, has no negative inputs. I can't take the square root of a negative number. I can't graph that here. So it starts on the positive 0 side. And this 1, 1 seems to be a number that pops up in all of these. And we see that the green graph is below the blue graph. And so now all of a sudden we get to that question we had last time, where we're summing up all this area, and what we're adding to the area is getting less and less and less. So our question is, well, is it enough? And we said that this one actually would diverge. Let's continue. 1 over x to the first power. We also said converges. So this blue graph, starting at 1, 1, if I start shading in all this area, this navy blue or purple graph, that area gets so tiny, so fast, but it's still enough that when I sum up the area, it diverges to infinity. Let's do one more. 1 over x to the second power. I'm just increasing the power by 1. That's in black. Again, it hits at that 1, 1. Let's see if you can see my mouse there. It hits at that 1, 1. If I start summing all the black area, then this will actually converge. And we found that sum last time. So there's this weird sweet spot right at this purple graph where that one converges. Sorry, that one converges. But anything, and therefore anything below it, like the black graph, would also converge. But I'm saying that wrong. 1 does not converge. 1 diverges. But anything smaller than that, like the 2, it converges. Anything bigger than the 1 will diverge. So we get into this comparison where I can kind of compare the areas of one function to the other, especially if I have the graphs graphed out like this. I can start to say, well, this area is convergent. This one's a little bit smaller, so I think it should converge as well. All right, let me go back to writing. And let's kind of talk about that some more. So I've got a question here. Does the integral of 1 over x to the 5th power converge or diverge? And we're talking about the integral from 1 to infinity. Now we know the answer to this. Because x is larger than 1, this will converge. So by the p-test, I'm done. But let's kind of go through the motions of what we're going to be facing today. So I want to know, what's going on here. Well, I know, just because it was in my notes last time, that the integral from 1 to infinity of 1 over x squared converged. And I know that 1 over x to the 5th power compared to 1 over x squared, can we tell which one's bigger or smaller? If I plug in a number like 2, well, 2 squared is 4, 2 to the 5th power is 32, so this one's definitely smaller. Now, when we start plugging in fractions, that's not always the truth. But we're talking about x values starting at 1 and increasing. So for all x values bigger than or equal to 1, I claim this is going to be smaller than 1 over x to the 2nd power. So 1 over x to the 5th power will always be less than or equal to 1 over x squared. And if 1 over x squared sums up to a finite number, it converges. Then something that's even smaller, well, that too should converge. So this idea of comparing integrals to one another and just making sense, is it really smaller, is it really bigger than, it gives us something we call the direct comparison test, which I have written above me, but I'm going to write it down and explain some of those symbols. All right, this is the direct comparison test. And this one is for improper integrals. There are other direct comparison tests. This one is for improper integrals. I'm just going to copy this down, but I'm going to let beta and tau be continuous functions over the interval a to infinity. So I'm letting beta and tau be continuous over the interval a to infinity. I have a little bar there. That's just such that I've got some more things I need to talk about, some specificities, where beta and tau are always positive. Going back to those graphs, I can do that real quick. All of these graphs, at least starting at 1, these were always above the x-axis, so they were always positive. So that's what I mean here when I say that beta and tau are greater than 0, and tau is at least equal to beta, if not bigger. So I'm letting tau be the bigger function and beta be the smaller. I'm going to upside down a just to say we're talking about, or like for all the x values that are greater than or equal to, I guess, a, that interval. In my example on Desmos, that a we're talking about is the 1, from 1 to infinity. So along values 1 or larger, where beta and tau are continuous functions, they're positive functions, and tau, if they're not equal, then tau is at least bigger, then we know some things. We know that if we're integrating along that interval, tau, and it converges, that is, the larger function converges like 1 over x squared, then the smaller function, like 1 over x to the 5th power, has just got to logically also converge. Little arrow, like implies. So the integral of a larger function that converges implies that the smaller function also converges. And we can say that similarly if the smaller function, beta, the beta function, diverges. So I have a function that's smaller than tau, and the smaller function adds up to infinity. Well, if I make that any bigger, it too will diverge. Oops. I wrote sloppy here, but I have it nice in type form above me. All right, so let's walk through a nice little simple example where we use this test to just determine if an improper integral converges or diverges. I want to know if the integral of 1 over 1 plus x squared over the interval 1 to infinity, if that will converge or diverge. All right, 1 over 1 plus x squared. Well, that sure does look a lot like 1 over x squared, which we know converges because p is bigger than 1. Yeah, 1 over x squared, which converges. So if I can say or somehow show that this is even smaller than 1 over x squared, then by the direct comparison test, it would also have to converge. Let me say that. I'm going to say by the p-test, we know that the integral from 1 to infinity of 1 over x to the 2nd power converges. If 1 over 1 plus x squared is less than or equal to 1 over x squared, then it will also converge. What tells us that? Well, the direct comparison test tells us that. So I'm going to say by the direct comparison test for improper integrals. Now I have to also dither about, is this thing, are they both continuous functions? They both have to be continuous, no asymptotes, no holes, no points of discontinuity. And they have to be positive functions over that interval. So I've got to dither about that for a little bit. And there's several ways you can dither about it. One way is just to graph the functions. So I can do that real quick. If you are having trouble just sketching them out, well, you can always just use a technology. So I'll quickly look at 1 over 1 plus x squared. Oh yeah, that's that famous like bell-shaped curve or normal curve. And then I'm also interested in 1 over x squared. 1 over x to the second power. That's what I'm comparing. So I'm kind of zooming in on starting at 1. Did I type those in correctly? 1 plus x squared. Yes, that looks right. All right, so yeah, the green function, at least to start off with, is definitely bigger than the blue function, where green is 1 over x squared. So it looks like graphically already that it's going to be smaller. I do need to prove it kind of algebraically. And I can tell that these are positive functions. They're above the x-axis. I can kind of zoom in if I need to, but these are going to be above the x-axis. And you can tell they are right on top of each other. That blue is a little bit less than, which is good news. But does that happen forever? So let me go back and play around with this algebraically, because I don't want to have to graph every single function in that great of a detail. Okay, but I've got my mind wrapped around it. I'm trying to show that this is somehow less than. One way I do it is to start with a true statement that no one can argue with, and I like to start with the denominator. So I think everyone is on board when I say x squared is equal to x squared. No one can argue with me there. I don't care if you're talking about inputs of 0, negative numbers, fractions, positive numbers. Any input squared will equal that same input squared. Now I'm choosing x squared because that's the thing they have in common, or that's the p-test version that I'm trying to equate. Now I'm going to add 1. I want an x squared plus 1. So I'm going to add 1 to the x squared on the left. And what is that going to do to my equal sign? I think if I add 1 to the left, maybe it's equal. I can at least equal to or greater than. That's going to be greater than or equal to my previous thing. If x was, whatever I'm putting in there, it's going to square it and make it either 0 or some positive number. So if I add 1 to the side, it should make it bigger. I think everyone's okay with it there. It's like I was saying something like 3 equals 3. Now 4 has got to be bigger than or equal to 3. Some of you may want to say, well, it's clearly greater than, but I'm being very, very loose. I'm saying it's greater than or at least equal to. At least equal to, because the direct comparison test says at least equal to. It could be bigger or equal to. All right, now, what would happen if I reciprocated both sides of the equation? That is, I put them under a 1. I'll go to my integer example over here. 1 over 4 compared to 1/3. They're not equal. Which one is smaller? Well, a quarter is less than 33. So this is less than or equal to. So when I reciprocate, it seems to flip that inequality as well. Careful though. What happens to a fraction between 0 and 1? So if I take 1 over 1/2, well, that actually makes it 2 and it makes it bigger. So this is not always true. So I've got to be very careful here. So I'm going to use that for all notation again. I'm going to say this will be less than or equal to that for all the values where x is at least 1 or bigger. So again, I'm not sure that this is always true. I know fractions are a little bit wonky when I square them and then divide by them. But I think reciprocating, it'll always be less than or equal to this thing, at least for positive numbers bigger than 1. I'm safe there. Well, look, I just did it. I just proved what I needed to prove. I said if that was smaller than this, then it would converge by the direct comparison test. And with some algebra and just kind of like logical thinking, I said, hey, it is always smaller than that. All right. So I'm going to say we're done. Therefore, Or I'll say, thus, by the direct comparison test, the integral from 1 to infinity of 1 over 1 plus x squared converges. All right, let's do that again. I think I'll get a sip of water. All right, let's try one that maybe isn't so obvious. But same question. Does the integral from 1 to infinity of 1 over the square root of x squared minus 1/100th, does that converge or diverge? All right. Well, first maybe I should dither about what this maybe looks like. I can tell if I plug in negative numbers, that is okay. It'll square it and become positive. So negative numbers are just like inputting positive numbers. And if I put in something like 2, well, 2 squared is 4 minus a little bit, I can take the square root of any positive number. The smallest thing I can plug in is 0. 0 squared does have a problem. 0 minus 1/100th, that's going to be a negative. But remember my interval. I'm not plugging in negative numbers. I'm not plugging in 0. I'm not plugging in fractions less than 1. The lowest thing I can plug in is 1. So 1 squared is 1. 1 minus a little bit will be a positive number, and I can take the square root of that and get an output. And I can tell as I get bigger and bigger and bigger, like 1000 squared is a really big number, minus a little bit. This denominator is getting bigger and bigger and bigger as I plug in numbers closer to infinity. And we know that that thing will approach 0. So it looks very similar to the graphs we have been graphing. Now, is it enough to converge, or will it diverge? So I think what I'll do is I'll compare it to something that I'm familiar with. What does that look like to you? The 1 over 100 is so minute, and we're talking big numbers like infinity. I don't even care about that. What function do you think we are going to compare this to? If you said 1 over x squared, you may have fallen for a trap. I'm thinking 1 over x. Let me show you what I mean by that. Ignoring the 1 over 100th. This is so insignificant. So I'm focusing on the big picture here. 1 over x squared. Well, wouldn't that just kind of like cancel each other out? Doesn't that go to 1 over x? I think what I would like to do is, this is very similar to 1 over x, so I want to compare it to 1 over x. Now I know the integral from 1 to infinity of 1 over x is going to diverge. Am I right there? 1, yeah. If it is less than or equal to 1, the power that is, it will diverge. There you go. P-test. Okay, that diverges. So I don't think we're going to use this top scenario here. If tau converges, then it converges. No. If we can show that maybe this is the tau function, and we can show that the given one is bigger than 1 over x. So if 1 over x diverges, and we can show that this one is bigger, then it too will diverge by the direct comparison test. Okay, now I gotta dither, I gotta make sure that these are always positive. I know 1 over x is always positive. This is too. No matter what x I put in there, I am going to square it and then take the square root of it. And 1 over some positive number is going to be positive. So yes, this is decreasing to 0, but it's always positive. So I need to worry about that. I'll say that. Both 1 over the square root of x squared minus a little bit and 1 over x are always positive. If I don't say this, then I can't use the direct comparison test. I also have to worry about it being continuous. I have issues with values less than 1. But yes, these are both going to be continuous over the interval 1 to infinity. Okay, so I've said that. Now, if I can just somehow show this is actually bigger, then by the DCT, I'll be done. Okay, I think I'm going to use my strategy of dealing with the denominator and dealing with the 1 over x. I'm going to look at that x, and I think I'll start with something no one can argue with me. X is equal to x. You have to agree with me on that one. Okay. Then how about this? If I square that value, because that's what I'm trying to get to, but then also square root it, how does that compare to x? Well, I mean, they should be the same, but let's do something like 2. If my input was 2. Well, 2 squared is 4, and the square root of 4 is a negative 2. Oh dear. But I think we're okay. It's still equal, especially if my input was going to be 1 and bigger. So if I plug in negative 2, negative 2 squared is 4. The square root of 4, is it a negative 2 or a positive 2? And is it the same as this negative 2 over here? I don't know, but I can do this. For all x's that are bigger than or equal to 1, this is equal. 1 and bigger, same thing. Now, I'm going to subtract a little bit. So if I take the square root of x squared and subtract something, how does that then compare to x? Is that going to make it smaller or bigger or no change at all? Well, if I subtract something, even if I'm square rooting it and making it a small amount, if I subtract something, it should be less than. Now we're talking big numbers. We're talking 5 gadillion, 5 bazillion, jajillions. So in the end, they're going to be so similar. But that minus 1/100th is just ever so slightly small. All right. Now I'm going to do my reciprocal trick. If I can reciprocate this thing, 1 over the square root of x squared minus a little bit, 1 over x, how does that affect my inequality? It's going to flip it, as long as I'm, again, talking about those big values. Okay, I've just done it. I have kind of shown algebraically and just making sure logically that that all makes sense, that this given integrand that we were given is always bigger than or at least equal to 1 over x. We know 1 over x diverges. Because this is bigger, it must also diverge. Quod erat demonstratum, QED. I've said all I need to say. Okay. That's the feel for this lecture. Now, I was able to compare the 2 previous examples because it was 1 over x and 1 over x squared. So I think I can use all of those 1 over x to some power. Those are tools in my tool belt of this comparison idea. Now, I want more tools. I'm going to do another improper integral that we can maybe add to our list. So I'm not using the direct comparison test here. I'm just old school trying to integrate from 1 to infinity this function e to the negative x. Just evaluate it. I want to know what's going on. Well, this is a nice 1 over e to the x function. I kind of think I know what that looks like. And yeah, it looks very similar. Let me just graph it real quick. One over e to the x. Oh yeah, I zoomed out. Zoom. Oh god. Let me get back to the origin. Probably should have refreshed it. There's probably a button somewhere to do that. But okay. This is e to the negative x, or 1 over e to the x, which of course, yeah, if I plug in 0, e to the 0 is 1, so 1 over 1 is there. But I'm only looking at this thing starting at 1, and then yeah, this is going to look a lot like those previous functions. Okay, so is it enough area to converge or diverge? If it converges, what does it converge to? Okay, improper integrals, the way we handle this is we introduce a dummy variable, I'll use t, and we also introduce limit notation. So I'm going to evaluate the limit as t goes all the way to infinity of the integral from 1 to t of e to the negative x dx. Well, I can integrate e to the negative x. That's e to the negative x with a negative out front. So I still have a limit as t goes to infinity of negative e to the negative x, and I need to evaluate this from 1 to t. I'm going to use the fundamental theorem of calculus that says I can plug in, well, I could pull out that minus sign. I think I will. That minus sign is acting as a coefficient inside a limit. That can be pulled out of the limit, so I have a giant minus sign on the outside. And I'm going to plug in a t, then plugging in a 1. I'll just clean this up a bit. I'm not sure if I can make it too much prettier. But this is 1 over e to the t minus 1 over e. The limit of a number is that number. So really I just have this. Direct substituting. 1 over e to the infinite power minus 1 over e still. Well, e to the infinite power is infinity. 1 over infinity, the biggest number I can think of. This limiting process is going to make that go to 0. So I have a negative 1 over e. Oh, so this integral converges. That area under the curve actually will add up to a number, a constant number, 1 over e. That's pretty cool. Okay, this is another function, another improper integral that we know converges. So I think we have something that kind of fits this first option here. So if I need to show convergence, well, here's a tool in our tool belt. So let me show an example where we use this. Let's look at the integral from 1 to infinity of e to the negative x squared. Now this is actually a famous integral that we cannot integrate. We don't have the tools to actually do it. But we can maybe talk about if it's going to converge or diverge. because it sure does look a lot like the previous one we just did. Let me graph this one too while I have Desmos up. So if I go 1, or let me just type it out like they have it. E to the negative x squared. I do want to see both sides of the y-axis. Yeah. This is that famous bell curve. This is a very trivial form of the standard normal model, sort of, kind of. It's the same idea. I've got this normal shaped, or this bell curve, and I'd like to integrate it. I'd like to find the area under that curve. I can't do it. For this example, I'm looking specifically at the area under, or starting at 1 and going under. So I'd like to add up all that area. Okay. And I claim we can't do it. But I think it can compare to something we do know. We know 1 over e to the x, or e to the negative x, converges from lecture notes, I guess. Lecture notes. It is going to be a continuous function. It's always positive. Same is true here. I just looked at it. It is always positive, and it is continuous. For sure, over the interval we're concerned with. All right. So if I can show that this thing is smaller than something that converges, then it too will have to converge by the direct comparison test. So if 1 over e to the x squared is less than or equal to 1 over e to the x, then it too converges by the direct comparison test. So now I just need to show that. All right. I think I'll do my trick where I look at the denominator. So I'm looking at e to the x, and this is the one I'm familiar with. So I claim e to the x will always be equal to e to the x. No one can argue with me there. Now if I square it, let's see what will happen. I think that's going to make it bigger. If I take e to the x and square it, how does that compare to e to the x? Well, that's debatable. I've talked about these fractions, but I think this is a good time to maybe show it. Let me use Desmos again. So I'm looking at e to the x squared and e to the x, not these reciprocal looking things. Just a normal e to the x squared and e to the x. Maybe this is not what I want to do. Oh yeah. Yeah, this is perfect. Okay. So in black I've got e to the x. In purple I've got e to the x squared. Notice from the purple, for the most part, is always bigger than the black. So ex squared is always bigger than the black function, except between 0 and 1. Those fractions, when you square them, actually make them a little bit smaller. So there is this one area where I can't say that that's always true. So this is why it's very important that I have to now say, okay. The purple one is always bigger, starting at 1 and then on out. So let me go back. So I would like to say that this is always going to be bigger, but we just showed there's this spot of the graph or it's not. It's actually less than. But for all x's that are at least 1, starting at 1 and bigger, this is actually going to be bigger. Now I'm going to do my reciprocal trick. 1 over e to the x squared will be less than or equal to the reciprocal here. 1 over e to the x. I'm done. I proved it. I showed it was less than. I stated that if it is less than this, which we know converges by some other form, the lecture notes, and I said they were positive and continuous, then by the DCT it is going to also converge. And now, by the way, we have this added to our tool belt as well. If I needed to compare a function to 1 over e to the x squared, well, I now have this. I know this converges. Every one that we do from now on in lecture notes and in the homework will just be another tool you have. All right. I'm going to do another example. This one, you just kind of need to see it once. Sticking with my interval, 1 to infinity. I'm going to put sine squared x up top and x squared down below. And does this thing converge or diverge is all I want to know. Improper integral, just asking if it converges or diverges. Well, I think I must be supposed to use the direct comparison test. So what should I maybe compare it to? 1 over x squared? Yeah, I agree, because that's what I've got down there. What happens to 1 over x squared? It converges. So if I can show that sine squared over x squared also converges, then I'm done here. All right, this time I'm not going to start with my x squared equals x squared strategy. I'm going to play around with that sine squared just a little bit. I know something about regular sine. No matter what angle I put in the sine function, it is bound between -1 and +1. I'm stuck between those range values as I wave out. Okay, well I need a sine squared. So I'm not squaring everything here. I'm just saying, well, what happens to these inequalities when I square sine of x? So if I, again, same question, if I plug in an angle to sine and then square it, well, the biggest number that will pop out of sine is 1. And when I square 1, that's still going to be 1. Any output that's a fraction, like sine of pi 6 is 1/2, 1/2 squared is still going to be less than or equal to 1. The root of 3 over 2 squared is still less than this. What about those negative values, though? Sine of a negative pi 6 is a negative 1/2. Oh, but when I square it, it becomes a positive number. So what's the lowest sine can get? All the negatives become positives. But sine of 0 is 0, and 0 squared is still 0. I think it's safe to say that sine squared will be stuck between 0 and 1. All right, so I'm just logically thinking about this. I'm not following some procedure that always works for this thing. I know I kind of want to compare it to 1 over x squared. I'm thinking about sine. I'm trying to get sine squared. What's going on here? I think like sine squared and 1 over x squared. 1 over x squared and sine squared over x squared is these two values divided by x squared. I'm going to go through and divide everything by x squared. Well, that's dangerous because x could be 0, and I cannot divide by 0. But, oh yeah, don't forget our interval. We're just talking about numbers 1 and larger. So dividing by 0 is no, you can't do that. Dividing by a negative number, that would flip the inequalities. Dividing by a fraction may not always make this true. But if I'm talking about values 1 and larger, then the inequalities will hold. 0 divided by that is still going to be 0. I'll have sine squared of x over x squared and 1 over x squared. Now look what I've got here. This thing I know, 1 over x squared I know converges. By the p-test. I know this is always positive and it is continuous. This will always be positive and continuous. And because 1 over x squared converges and this is less than that, or because sine squared of x over x squared is always less than or equal to 1 over x squared, we know, like, therefore, the integral of sine squared x over x squared from 1 to infinity converges by the direct comparison test. Alright, so as you work through these direct comparison test problems, there's a lot of writing involved. You've got to talk about it being positive, and you have to talk about it being continuous. Make sure you do that. You have to state the direct comparison test every single time. I've done it different ways, but you've got to say, if this function converges and this one is smaller, so it will also converge. Or this function we know diverges because of whatever reason, and this one's bigger, so it also diverges. So state the direct comparison test every single time. And then you have to also, the hard part for these problems is doing the weird algebra logic maneuver of making it less than or equal to, or greater than or equal to. That's the hard part. This is the new part we may not have ever had to do before, of just logically, algebraically show that one function is larger or equal to or smaller or equal to another function. Go through my solutions to see more examples, and then tackle the homework, and I'll see you in the next video.